Some weapons try to slip past the radar screen. Others become more effective the moment the radar activates. This is exactly how radar emitters were targeted in a mixed attack of 6 ballistic missiles and 29 drones at Prince Sultan Air Base in Saudi Arabia this March 27th, according to the Associated Press. The strike wounded at least 10 to 12 U.S. personnel and damaged several aircraft on the ground, including refueling tankers. While public reporting has not identified the drone model, the attack profile points most strongly to one possibility. A mixed package of ballistic missiles and drones is exactly the kind of attack where a faster, jet-powered one-way drone like the Shahed 238 becomes relevant. Not because it hits harder, but because it arrives sooner and compresses the defender's timeline. The older Shahed 136 is the baseline threat most operators already understand. It's a propeller-driven, piston-engine one-way attack drone, usually credited with speeds of roughly 95 to 120 miles per hour, and a range of 930 to 1,240 miles. Its advantage is not speed, but cost and scale. The Shahed 136 is dangerous because it's cheap enough to be used in numbers, forcing the defense to solve the same problem again and again. The Shahed 238 keeps the same basic idea, but with some very important upgrades. Instead of a piston engine, it uses a turbojet. Secondary reporting on the system describes it as a development of the Shahed 136, with a stated speed of 500 kilometers per hour, or about 310 miles per hour, a range of 1,200 kilometers, or about 745 miles, an operational ceiling of 30,000 feet, and roughly 2 hours of endurance. It trades less reach for much more speed, and much less time for the defender to react. It's still far slower than a subsonic cruise missile like JASSM, but it's roughly 3 times faster than the familiar Shahed 136. That speed difference matters because air defense is a timing problem before it's a firepower problem. A faster jet-powered drone shortens the time to detect, classify, assign, and engage. The system may still be detected, but the margin for sorting tracks, assigning shooters, and taking a second shot gets noticeably smaller. That's why a Shahed 238 type system becomes interesting in a mixed strike, especially one built around ballistic missiles and drones arriving on different timelines. Aside from that advantage, the Shahed 238 is also reported to exist in multiple configurations. The basic version appears to rely on satellite and inertial guidance. Other reported variants add an electro-optical or infrared seeker, and interestingly, a passive anti-radiation or radar homing mode. What makes it such a threat is that a passive radar homing drone does not have to reveal itself by transmitting. It waits for the defender to emit first, then it homes in on those emissions. In effect, the radar meant to detect the threat can also help guide it in. That does not mean this mode was used in the Saudi strike, nor does it prove a Shahed 238 was present there. But if such a variant is real and operational, a mixed missile and drone attack is exactly the kind of environment where it could have the most leverage. That's because ballistic missiles force immediate defensive attention. Search radars, tracking radars, and fire control systems all have to work harder and stay active longer. The air defense network becomes more visible as it becomes more active. In that environment, a drone that can home in on emissions does not need advanced stealth to matter. It doesn't need a huge warhead either. The Shahed 238 appears to remain in roughly the same payload class as the Shahed 136. No official warhead figure has been released, but at about 380 kilograms gross weight, or around 800 pounds, it's clearly not in the same category as larger cruise missiles carrying several hundred kilograms of explosives. In other words, this remains a compact one-way attack drone, not a small ballistic missile. Economics is part of the threat. Open source estimates for the Shahed 136 often range from tens of thousands of dollars. However, numbers vary widely, depending on whether the estimate refers to production cost, export value, or assembled kit price. The Shahed 238, with a turbojet and more complex guidance options, is widely understood to cost more, but there's no solid public unit price reporting for it. Even so, no matter the cost, the value of a drone is not that it needs to destroy a hardened bunker to be effective. It only needs to damage something worth far more than it is. Follow-on reporting and imagery from the Prince Sultan Air Base strike point to an E-3 Sentry being hit, with later coverage describing that aircraft as effectively destroyed. That's a much bigger loss than the destruction of a single airframe suggests, as this is one of the few aircraft in the US inventory built to turn scattered sensors into a single air picture. Built on a modified Boeing 707 airframe, it's large enough to carry not just the radar dome people notice first, but the crew, electrical power, mission consoles, and battle management systems that make it an airborne command post. The Air Force describes the E-3 as a platform for surveillance, target detection, tracking, and command and control. Its AN/APY-1 or AN/APY-2 radar is commonly described as reaching beyond 250 miles, with low-flying targets detectable at more than 200 miles and higher altitude targets farther out still. From altitude, the E-3 sees beyond the line of sight limits that constrain ground-based radar, pushing the defensive horizon outward by hundreds of miles. Without it, the force loses sensor reach, warning time, and part of the airborne command layer that keeps the air picture coherent. A ground radar can be powerful and still be limited by terrain and the curvature of the Earth. If the sensor is moved to a large aircraft at tens of thousands of feet, then the horizon moves with it. That creates earlier warning, cleaner tracking, and more time to react. The loss would also make coordination harder. The E-3 is not just a radar platform. It's a control node that helps direct fighters, deconflict airspace, cue intercepts, and maintain a common operating picture for the wider force. A typical sortie carries a flight crew of 4 and a mission crew of 13 to 19 specialists, and it can remain on station for about 8 hours without refueling, and with aerial refueling much longer. That means a strike package, tanker track, or defensive counter-air mission does not have to rely only on each aircraft's onboard sensors. The E-3 extends awareness across the network. Remove it, and every other platform becomes a little more isolated and a little more dependent on its own radar crew and line of sight. The E-3 fleet is old and small. Production ended decades ago, and recent reporting says only 16 US E-3s remain, with 6 reportedly at Prince Sultan at the time of the attack. That does not mean all are equally available at any given moment. Aging fleets rarely work that way. So losing one is not like losing one F-16 out of a very large global inventory. It's closer to losing a high-value node from a shrinking fleet that was already living on borrowed time. That makes the strike more consequential than the destruction of a single airframe might suggest. The replacement problem makes it worse, since the E-3 was already being phased out in favor of newer airborne early warning systems, and recent reporting has pointed to the E-7 Wedgetail as the intended successor, though political and budget fights have slowed that transition. Either way, replacement is not immediate. An AWACS is not replaced the way a truck is replaced. The real capability is not just the aircraft, but the system behind it. The radar, the mission crew, the data links, the maintenance infrastructure, and the training pipeline. The airframe is only the visible part. The Air Force once listed the E-3 at $270 million in 1998 purchasing power. Recent reporting says the nearest replacement, the E-7, could cost more than $700 million per aircraft. So the real loss is not measured in dollars. It's measured in warning time, coordination, and the shared air picture that keeps the rest of the force from fighting half-blind. When a drone worth a few $1,000s can put millions in aircraft and equipment at risk, a military campaign can drain even the largest defense budget on Earth pretty quickly. For a force defending ships, air bases, and high-value support aircraft at scale, that exchange rate becomes a problem quickly. The issue is not only whether the target's destroyed, but whether the defense can afford to keep responding this way. That's why one of the Pentagon's clearest answers to the drone problem is now a laser. The system drawing the most attention is Helios, or high-energy laser with integrated optical dazzler and surveillance. Lockheed Martin describes it as a 60-plus kilowatt class laser weapon, integrated into the ship and the combat system. Its stated missions are counter unmanned aerial systems, counter fast inshore attack craft, long-range ISR support, and dazzling hostile sensors. In plain terms, it's designed to detect, disrupt, and destroy. A laser system focuses electrical power and turns it into a beam of light. If that beam stays on target long enough, it can burn through sensors, damage control surfaces, overheat critical components, or force a drone out of the sky. shot arrives at the speed of light. There's no flight time to manage, and no intercept geometry in the usual sense. The limiting factors are power, beam control, target tracking, and dwell time. That's a different problem from magazine depth. The drawback is that a laser pulls directly from the ship's electrical system. Even if rated at around 60 kilowatts, Helios' system draws significantly more than that once losses and cooling are accounted for, often well over 100 kilowatts during sustained firing. That power comes from the ship's generators, and those generators burn fuel. So the cost depends on how long the beam stays on. Even so, it remains cheaper than missiles. Recent reporting has described the per-shot cost as ranging from a few cents to around $1, depending on dwell time, power draw, and the method of calculation. BGR and defense reporting both point to Lockheed Martin working on 300 kilowatt class systems, which would be roughly 5 times the power class of Helios. This would mean it's designed for harder, faster, and more demanding threats. In late 2025, Scale-Directed Energy was named one of the Defense Department's 6 critical technology priorities. The reason was that high-energy lasers and high-powered microwave systems offer a much cheaper response to mass attacks like drone raids and missile salvos that force defenders to burn through their own inventory. Helios has also been delivered to the Navy and integrated onto USS Preble, an Arleigh Burke-class destroyer. This means the system has moved beyond testing and into deployment, with public reporting tying it to the same operational theater where Iranian drones and missiles have been a persistent threat. Whether Helios has recorded confirmed combat kills in this war is not yet publicly verified by primary military sources. Still, secondary reporting has linked Helios to several Iranian drone shootdowns, even if those remain unconfirmed by primary sources. Military Times reported in March that Pentagon officials want to field directed energy weapons at scale within 36 months. If power, beam control, and targeting continue to improve, the next step is wider integration across the force to reverse the exchange rate. Iran is now showing signs of missile reach, far beyond the limits long associated with its arsenal. For years, the public number attached to Iran's ballistic missile force was about 2,000 kilometers, or roughly 1,240 miles, which already covered most of the Middle East. In March, that assumption was challenged when the Jerusalem Post reported that Iran fired a shot which traveled roughly 4,000 kilometers, around 2,500 miles, toward Diego Garcia. If that figure is accurate, the demonstrated range has doubled. A missile force built around regional reach suddenly started looking far more threatening. The explanation most often raised in the reporting is staging. Former IDF Air Defense Chief Ron Kohav said the launch likely used a 2-stage satellite-like launch process. This is one of the clearest ways to move from a familiar medium-range missile profile to something much longer-legged. While a single-stage missile burns, coasts, and falls, a multi-stage system sheds dead weight and keeps accelerating. That's how the same country goes from threatening nearby capitals to threatening targets thousands of miles farther out. If this capability is real and repeatable, it would put London, Paris, Berlin, and other European capitals within range. The interesting part is that none of this necessarily requires a visibly revolutionary weapon. Kohav pointed to 2 possible explanations for the shot. One is a modified R-27 type missile, a Soviet-designed ballistic missile, originally built for submarine launch and designed for a much longer range than the missiles Iran is usually associated with. The other is a modified Khorramshahr-4, one of Iran's heavier long-range ballistic missiles, normally discussed in the 2,000-kilometer class. Neither explanation requires a completely new weapon. Both could result from getting more range out of an existing missile by changing the engineering, adding another stage, reducing the payload, or adopting a more efficient flight profile. Kohav said an R-27 type missile would typically carry a warhead of around 1.5 to 2 tons. However, if the payload's reduced, the same missile can sacrifice destructive power for range. One of the most important contextual clues is Iran's Cairn-100, the solid-fuel 3-stage rocket used by the IRGC for orbital launches. In September 2024, Iranian state media said it placed the Hamran-1 satellite, weighing 60 kilograms or 132 pounds, into an orbit of about 340 miles above Earth. That same report says the Karen 100 was used again in January 2026 for another successful launch. The U.S. intelligence community's 2024 Worldwide Threat Assessment warned that Iran's development of satellite launch vehicles would shorten the timeline for developing an ICBM if it chose to do so. While a space launcher and an intercontinental missile are not identical, the concern is that progress in one area reduces technical risk in the other, because both rely on multi-stage flight, propulsion, separation, and guidance. That still does not prove the 2,500-mile shot was a Karen 100 derivative, but it does show that Iran has been working with a technology base that could support longer-range missile development. If that interpretation is correct, then a force that can threaten more distant targets gains something important: choice. It can put bases, logistics hubs, and rear-area infrastructure at risk that were previously outside the fight. It can also force defenders to spread missile defenses across a much wider map. That would not require matching the US or Israel's systems. A longer-range approach does not need to win the air war outright. It only needs to make the defended area larger, the warning time shorter, and the cost of protection much higher.